Hi, I'm Henry Segerman.
And I'm Tom Crawford.
And we made this video of us getting lost in some strange multiply connected library. There's a link in the description to that video, so go and look at that first because we're going to explain how we made it here.
Okay, so what's going on in this library? We didn't actually find a multi-dimensional library, that was just some video trickery. However, we did really film at the library here at St Edmund Hall in the University of Oxford. However, we used some clever maths to create multiple copies of the library, which is what you saw in the video.
In reality, we were walking around a single real-life library, whereas in the video it looked like there were multiple copies of each real location in that space. The mathematical term here would be to say that the multi-library is a covering space of the real-world library. Here's a simpler example of this situation. So I've got this curved around spiral or helix, and I've got a map down to the circle, which is just sort of cast a shadow down from the helix to the circle. And this has the nice property that if you look at a little bit of the helix up here, then the thing that it maps down to on the circle looks the same. And that's the same for any little bit of the helix, sort of looks the same as the bit of the circle that it maps onto.
It's a bit like a multi-story car park. When I walk all the way around the loop, it looks like I'm in the same place, but I'm actually in a different position, just one level up. You can think of the multi-story car park as a covering space for an infinitely looping car park from which I can never escape.
Here's another example. Rather than a circle downstairs, we're using this theta graph. So it's got a blue arc, a red arc, and a white arc. And in the covering space upstairs, you've also got blue arcs, red arcs, and white arcs. So what do we need to have happen for it to be a covering? We need that anything upstairs, its shadow has to sort of look the same. So this vertex here where blue, red, and white meet has to map down to blue, red, and white meeting, and it does. Same thing with the other vertex. So these two vertices here both have to map down to this, and they look the same. The arcs are a little bit more complicated. The blue arcs up here map down to the blue arc here, that's fine. Reds map to red. The white's a little bit more complicated. There are these two arcs here. These actually have to cross over when they go between the two levels upstairs. But they still have to, so the white arc has to go from the top right to the bottom left vertex. And here again, it goes from the top right on this upper level to the bottom left on this lower level. Whereas the other white arc goes from the top right on the lower level to the bottom left on the upper level.
And this theta is in fact the library. We have the three paths that we walked along, either side of the main bookshelf and behind the table.
This is the covering space that we used for the video. So in the real world library, we had three arcs corresponding to the three paths we could walk around between the bookshelves. So, well, this was between the two bookshelves, this one was between the bookshelf and the table, and this one was behind the table. So the table's here, the bookshelf is here, this is where the football ended up getting split into pieces. And then upstairs, when we sort of unrolled it into this cover, we got this much bigger, more complicated space. So for example, Tom started out at the doorway about here, which on our map was up here. And then he walked between the two bookcases to here, where he met me up at the top of the picture. And then we talked about some things. And then we both walked around behind the table where we rolled the football and destroyed it and so on. And that was going over here. And there's sort of, this path here, there's no choice in what I end up doing correspondingly up here. I have to go along, or Tom has to go along all the way along white and then halfway along blue. And if I start up here, I have to go all the way along white and go halfway along blue. I can't turn down red because we just didn't go that way. So the path here determined the path up here, and then we kept going and got lost and eventually tried to find our way back to the doorway that actually exited to Oxford. Maybe I'll put a circle around the vertex that had the door in it. So where is that upstairs? So Tom started here. It's the blue, white, red one. So this is not the right vertex. That's the one on the other side. This was a doorway. and then this was a doorway, and that was a doorway. And so we ended up exploring all three of the other doorways, and well, maybe Tom never got out.
Now that we've revealed the secret map that we were following to make sure that we kept getting lost, you're probably wondering how exactly did we make the images that you can see in the final video.
That's all down to this spherical camera, which I used to record the video. It has a fisheye lens on either side, and the two of those allow it to capture the entire sphere of data around it. So I have some code which then takes that sphere of data and for each frame of the video transforms it to turn it into the covering space. So the mathematics there is the sphere you can think of as the complex plane plus one point at infinity, and then applying various complex functions, you can do transformations to the spherical image, including doing this kind of covering transform. I made a video with Vi Hart using the same sorts of techniques, using a cubing transformation to make our video Piece for Triple Piano. There's a link in the description, so you can check that out as well.
The function that we use to transform the sphere in the library video is given by f of z is equal to z squared plus 1 squared divided by 4z multiplied by z squared minus 1. Which of course looks very complicated, but ultimately this is just creating 4 copies and then moving around points on the spherical camera image to produce the multi-dimensional library which you can see in the final video. Now I'm not going to explain in full detail how this particular map works, but I will show you what's going on with a simpler example in the form of the map g of z equals z squared. So this is taking an input, let's say z is equal to a plus ib, a complex number, and then the output is the square of that complex number. And if we do that expansion of the brackets and simplify a little bit, we get a squared minus b squared for the real part, and then that's plus 2ab times I for the imaginary part. Now the issue here is if we want to go back to our start point. So suppose we are given the output, we're given the value of z squared, which of course has to have this form, and we want to work out which point z we started from. Even with the real numbers, we have multiple square roots. So for positive real numbers, if we were to square root them, we would get both positive and negative branches of the square root function. And something similar is going to happen in the complex plane, but it's a little bit more complicated. So first, let's define what we mean by a complex square root, and I'm going to do this using logarithms. So we're interested in the inverse function, so g inverse of z is going to equal the square root of z, which of course we can rewrite as z to the power of a half. Now I want to define this in terms of logarithms, so I'm going to use the relationship between exponential and log. And I can say this is actually the same as the exponential of a half times the log of z. So using the properties of logs, this half can go inside and it becomes z to the half, and then exponential and log cancel each other out, and you get back z to the half or the square root, which is what we want. So this means if we're going to understand the square root function, we actually need to understand the complex logarithm. And you may have noticed I've used a capital L on the log here, and that's to indicate that this is indeed the complex valued logarithm function. Now, to investigate this, we need to look at the polar form of a complex number. So, if I have a randomly selected complex number, so z is a complex number, then we can say that z is equal to r e to the I theta, where r is what we call the modulus of z, which is the distance from the origin, and theta is what we call the argument, or arg z, and this is the angle with the positive x-axis. So showing this on a plot, what we might have for a number in the positive quadrant, suppose we have a z here, this is going to be our distance r, and then this is going to be our angle theta, the angle we make with the positive x-axis. Given this form of a complex number z, I can now take the logarithm in the usual way. So if I had to calculate now log of z, then if z is r e to the I theta, I can say, well, that is log of r e to the I theta. Now I have a product r multiplied by e to the I theta. So from the properties of logs, log of a product, log of ab, is equal to log of a plus log of b. So that's actually the same as the log of r plus log of e I theta. But of course, as before, the log and the e cancel out. So overall, I can say this is the same as log of r plus I theta. And this may well be a valid way to define the complex logarithm. Now, the reason I said this may well be valid is it seems very sensible, and all we've really done is use the polar form of a complex number and then some properties about logarithms which we know to be true. However, this theta is not unique. So if I go back to my diagram here and my point z, so this is at an angle theta with the positive x-axis. But I can, of course, start here and go all the way around, like so. So that would be theta plus 2 pi, would be another way of writing out the argument of this particular complex number. And I could, of course, go around again. So it could be theta plus 4 pi, theta plus 6 pi, even theta minus 2 pi. I can add on, in fact, any multiple to n pi for n an integer. So any integer multiple of 2 pi added to theta is also true. And this creates a little bit of a problem because suddenly, because theta is not unique, we've actually got here something which is called a multifunction. Now, in order to overcome this issue of non-uniqueness, we limit the range of theta using something called a branch cut. And it is these branch cuts which give rise to the multidimensional nature of our multidimensional library. So here is a simple example with the function z to the half or the square root function. The way it works is as follows. We draw a diagram of the complex plane and we decide where we are going to take our branch cut and, as such, how we are going to limit the range of theta. So if we suppose that our angle theta has to be from 0 to 2 pi, then what we're really doing is saying we're taking our branch cut along the positive real axis. Now what this means is a point a tiny bit above the axis, so let's suppose a real number, because we're on the real axis, but just a tiny bit above, so maybe epsilon I added to it. That would have a value of theta equals 0, and a point a tiny bit below this axis, so for example a real number x minus epsilon I, this would have a value of 2 pi. And we have this discontinuity in our function, the argument of our complex number. Of course, everywhere else on the diagram, over here or down here, these are all valid values of theta, exactly as you might expect, and we would go around like so to get the full range of possible theta values and the full 2 pi range of the value of our argument. Now, to see how the branch cut works when calculating our square root function, we're going to look at a positive real number. So let's suppose that z is equal to x, which is a real positive number. And what we're going to do, as hinted at by the diagram, is actually consider these two cases. So we can approach this from above where theta is 0. That will be case A. Or we can approach it from below when theta would be equal to 2 pi. Now, let's calculate in these two cases what the square root of x will turn out to be. So, in case A, we have z is equal to x. So, for our polar form, that would be z equals x times e to the I 0, which is, of course, just x. So if we now substitute this into our formula over here, we say this is the exponential. So we would say z to the half, therefore, is equal to the exponential of a half times log of z, but log of z is log of r plus log e to the I theta. Theta's 0, so that disappears. It's log of r, so it's just a half log x. So now using the properties of logs, that is just x to the half, and we can see this is a positive number. So that is positive. Now for case B, where theta is 2 pi, this one here, we again follow the same formula. So z is x e to the I times 2 pi. We then use our logarithm thing over there for z to the half. So z to the half is now equal to exponential of a half times log of z. But log of z is this, so that's going to be a half of log of x, that's our r value, plus I theta, so plus I times 2 pi inside there. Now, what we've got here when we simplify by multiplying through by the half is going to be the exponential of log x to the half. And then we've also got multiplied by the exponential of I pi. So we've divided by the 2 there, or multiplied the half by that I 2 pi to get e to the I pi. Now once again, the e and the log cancel, gives us x to the half, but we also have e to the I pi. Now e to the I pi is actually a very famous identity. This is Euler's identity. So Euler's identity tells us that e to the I pi is equal to minus 1. And this, as I say, is Euler's identity. So using this down here, we can see that this gives us a minus, and then we get minus the square root of x, which is, of course, now negative. So we can see that in these two cases, either side of our branch cut, we're actually getting the positive and negative square roots. As well as getting the two solutions we were expecting, we can also see how to distinguish between the positive and negative branches of the square root function. It just depends which side of the branch cut we are on. And importantly, as we move across the branch cut, we jump from one copy of the function to an identical copy, but on a different branch of the multifunction. So what this all means in the context of the multidimensional library is that crossing a branch cut does not return us to where we started, but instead creates a copy or different branch of our function, which we then move to.
In the library, the trick with the football duplicating itself was the result of it passing through one of those branch points that Tom's talking about. In fact, there were 3 branch points in the library. There was one up on the ceiling above the camera, there was one directly below the camera on the bookshelf that it was standing on, and there was another on the table where the magic with the football happened. So we had to actually be pretty careful when we were walking around to not get too close to those branch points, otherwise we'd get duplicated as well.
And that's it. As you can see, I eventually made it back to Oxford, though Henry, where are you right now?
I'm at a place called ICERM, which stands for the Institute for Computational and Experimental Research in Mathematics, where we've been doing an entire semester on illustrating mathematics.
How appropriate. I'm glad you made it to where you wanted to be. I'll see you next time.
Bye for now.
A huge thank you to Henry for putting this all together, and a big thank you to all of you for watching the videos. If you have enjoyed them, please do consider subscribing to my channel, Tom Rocks Maths, and also to Henry's channel, Henry Segerman. We'll see you soon.